Okay, thank you, and I'd also like to thank the organizers for asking me to come and talk today. Most of you probably don't realize how dangerous bioinformatics is. I'd just like to show you an example of the types of injuries one can come from working on their computer all day. As I broke my right arm a few weeks ago. So today I'm going to talk about, I'm going to actually follow on a little bit from Jeff's talk and talk also a little bit about the 1,000 genomes, but from a slightly different perspective in annotating and trying to understand these catalogs of human variation that we have and taking this forward to really the expected large scale of data generation that is nearly certain to arrive over the next 5 to 10 years. There's a number of challenges to making this possible. And I'm going to start with just the challenges of creating and managing the variation data. So the 1,000 Genomes Project is, as far as I'm aware, the biggest distributed data collection project in biology's history. Now, it doesn't really compare to distributed data analysis projects like have gone on in high energy physics or in astronomy, where we also have an aspect of distributed data collection. But even today, most biology projects that are large scale do the sequence creation in one place and the analysis in one place. June gave nice examples of that, about how the BGI does a lot of work in a single place with a lot of data. In this case, we did a lot of work with a lot of data that came from multiple places, and we did the work in a lot of places. And that caused some interesting challenges. Of course, we know that large-scale genome sequencing is increasing. It wasn't that long ago that the Human Genome Project, which some people called biology's moonshot, was completed. That was only a decade ago. It cost, of course, as was mentioned this morning, about $3 billion. But today, because the prices are so inexpensive, we have these large-scale projects, the 1,000 Genomes Project, the Cancer Genome Consortia. We get to see stories about Ozzy Osbourne's genome on the front page of the Times in London, and a whole host of other celebrity genomes, which might be the worst thing to come out of this technology. But of course, it's not going to stop here. Soon we're just going to have thousands of genomes, thousands of cancer genomes. Jeff talked about the UK 10K project. Next generation sequencing technology is already in common use in diagnostic labs and more. And so we end up with just very large amounts of data, much larger amounts than biology has ever had to face before as a field. So I'm going to start with some examples from the 1,000 Genomes Project. Jeff discussed this a little bit. The paper came out yesterday. If you haven't read it, I encourage you to do so. It was released under a Creative Commons, no commercial use, share-alike license, which I think is the first time nature has ever done that. So you can take the paper and give it to anyone you want. And that's the license that nature has given us. The goal here was to create a catalog of human variation, and it's about shared variation. Jeff mentioned this. So this is variation that occurs in the population and is less concerned about variation that is specific to an individual. And the strategy for doing this is low coverage over many samples. So back when the project was originally conceived, the plan was to do 1,000 samples at about 2x coverage. And the plan was to take about 3 years to do that. As it turned out, technology increased dramatically, and we also discovered that, in fact, 2x coverage was not the ideal kind of sweet spot to find the information. It turns out to be between 4 and maybe 8x coverage on population sizes around 400. And so the main part of the project is built onto that assumption of subpopulations or different populations around the world of 4 to 500 at 4 to maybe 6x coverage. Of course, the pilot project has done a lot of work to evaluate and pioneer methods for sequence analysis and variation discovery. It seems very, very simple to do variation discovery in resequenced genomes, but in fact, it's actually very difficult to do it at high accuracy. If you just think about it, one could get all the variants in a genome right to 99% accuracy by just saying there aren't any. And so to go through carefully and find out where the variants are is a big challenge, and to get them all right. Structural variants continue to remain a problem. The project has done a lot of work to try to access this, but they continue to be a challenge to discover, especially from the types of data being discovered or being generated in the 1,000 Genomes Project. So I discussed a little bit about our original plan, which was developed in September 2007. Of course, the whole reason that this plan came about was because sequencing costs had dropped dramatically from the days of Sanger sequencing. And so the plan was about 6 terabases of sequence. It was going to take about 3 years to generate it. Well, so in reality, by the time we started generating data in the first part of 2008, we'd produced 4 terabases in about 6 months. And the dramatic reductions in sequencing costs continued. And in fact, in some ways, they accelerated. At the same time, many more samples became available. So the limitation on the 1,000 Genomes Project, which is now up to about 2,500 samples hoped for by the end of 2012, the limitation is not the sequencing capacity. The limitation is the collection of these samples and their transformation into lymphoblastoid cell lines, which are used in the project. So right now, the plan for the project is 2,500 samples at least 4x coverage. What we're seeing so far is that the data is coming in at about 6 or 7x coverage, and I think that's just going to continue to go up. That 7.4x is the raw coverage, and once we do the mapping, it's between 6 and 7x coverage. So this is meant to increase in the data size over what we originally planned for of between 8 and 10 times. And when someone like me goes to write a grant and you have an idea of how much data is going to be generated and suddenly 10 times more data comes in to be generated, that makes one kind of uncomfortable in the world of bioinformatics. So there were 3 pilot projects. Again, Jeff mentioned these, to deep sequence 2 trios. That's not going to be part of the main project. And then the low coverage sequencing to evaluate the methods of using low coverage data for population variation discovery. It's important to note that basically all of the data that's reported on in the paper that came out yesterday was generated in 2008. And so it's not tremendously representative of the type of data that's now available from the Illumina GA2s or from the HiSeq machines. The reads are much longer. You get much more data from them. And in fact, the data quality is much higher in many cases. So what this means is that some of the methods that were developed in the pilot project to in some ways cope with the data that as it existed in 2008 aren't quite as necessary today as they were back then. So you may have noticed that there's companion papers available in Science and also in Genome Research. There's a whole host of other companion papers in progress. And the full project data collection and analysis are underway. So this is just a couple of figures from the paper. This is about SNP discovery. There was about 15 million SNPs identified in the pilot project. Most of the SNPs, of course, or most of the common SNPs had already been seen. But of the novel SNPs, as one would expect, 84% of these were in a single population, and only 4% of the novel SNPs, being defined as not in dbSNP build 129, were found in all of the populations. So I mentioned already the difficulty in getting accurate variant calls from resequencing data. The false discovery rate for the SNPs in the 1,000 Genome Project was set at about 5% for the SNPs and about 10% for the small indels. This means that there's still a lot of false positives, and in fact also certainly false negatives in the SNP in these sets. So although the 1,000 Genome set is the most cleanly ascertained as far as the whole genomes, it's still an imperfect set and something that we continue to work on for these data. Not surprisingly, genome-wide SNP distributions vary. You see high variation rate in places that one might expect, including the HLA region on chromosome 6, as well as most of the telomeres. There's also notably low variation in certain places. One of the places is the relatively highly conserved region on 3p21. Jeff showed this, or a similar slide to this already, about the value of additional samples for variant discovery in a low coverage method. And essentially what it means is by the time you get to 220 low coverage individuals, you end up with about 99% of the synonymous variants. And by the time you have 320 low coverage individuals, you end up with about 98.5% of the non-synonymous ones. So the pilot project, again, only covered 180 samples. These were from the HapMap populations. The extension, which is ongoing now, to about 1,100 samples, I think we're at 1,044 samples currently at greater than 10 gigabases of sequencing coverage. Includes additional European populations as well as African, East Asian, and admixed American populations. By the end of 2011, assuming that all the samples arrive, we will have the complete set of 2,500 samples, which will include additional African populations, additional admixed American populations, as well as South Asian populations, to give us a large representation of not only human variation, but also of variation associated with the world's population. So this is just an update of the number of bases that we've taken into the project so far, and this is current as of Monday. Available on the FTP site is 22.6 terabases of sequence. If you include some of the data from the pilot project, this takes us to nearly 25 terabases of sequence, which is about 8,600x total coverage of the human genome sequence. The data increases pretty rapidly. In the last 2 months, we've added over 6.5 terabases of sequence, and it just keeps coming. As long as the samples are available, the data for this project comes very, very quickly. So to put the scale of data in perspective, I started out talking about that this project gives us large-scale data, larger than we've ever tried to manage in a distributed way in biology. Back in April 2008, when the 1,000 Genomes Project started, the EMBL GenBank archive had 235 gigabases of sequence. That represented, and the trace archive, which at the time had about 1.4 terabases of sequence, pretty much the complete sequencing output of Sanger sequencing and other data sets as well, up to April 2008. Of course, just in the last couple of months, we generate 235 gigabases every 2 days just in this project. As June noted, and in fact, all you have to do is look at the maps of the sequencers deployed around the world. This is only a tiny fraction of the worldwide sequencing capacity. And so we now have in biology those data sets that it used to be just our friends in physics and astronomy had to deal with. And we've dealt with them in very different ways than the people in physics deal with large-scale data. So when the Large Hadron Collider at CERN was being designed back in 1990, it was about, they had a time frame of about 15 to 20 years before it would go online. They knew how much data they were going to generate, which was about 15 petabytes a year. And they looked at the commercial internet that existed in 1990 and decided it wasn't good enough for them to transfer that much data around. So what they did is they built the LHCnet, which is a giant super-powered version of the internet that allows them to transfer data all around the world, from the point source collection at CERN to the 11 tier 1 data sites. So in biology, we rarely know how much data we're going to generate next week because of the advances in the sequencing technology. And so we've built no infrastructure at all. We use the commercial internet. We compete with people downloading music from the iTunes Music Store, from the BBC iPlayer, from whatever else is out there. And we just try to transfer the data around as best we can. It's honestly surprising, given all of that, that this works at all, much less that we managed to get publications out at the end. So the data is available. Anyone can download it. A lot of people do. We just recently ran the stats, and something like, between the two FTP sites, something like 3 petabytes of data have been downloaded in 2010. So on the 1000genomes.org site, we have regular news about the project. It's about 90 terabytes to download the entire data set if you want it from one of these sites. Now, of course, it's mostly in data formats that we invented in the project. And so if you're not in the project, you've maybe never heard of them or haven't used them before.